people here. I'm a MPI user, and yeah, I'm going to be going through some of the work I've done to develop a package for quantum algorithm research. Now, I think many people here are familiar with quantum computing, but just to lay the baseline, right? So we're talking about quantum. We're talking about doing computation using information that's encoded into the amplitude and the phase of quantum states. And our basic level of, or basic unit of information is a qubit. And we want to do this because, thanks to superposition, we have access to an exponentially larger representational space. And, in that space, the goal is to manipulate entanglement, interference, and superposition to get a useful result. Now, one of the applications that is often brought up as a promising near-term application of quantum computing is combinatorial optimization. And simply put, that's just the challenge of trying to find the best combination out of a certain number of elements in a finite set that are equipped with a cost function that'll map from a particular combination of your combinatorial variables to some scalar cost function. More formally, we would say that we're representing our solutions as vectors, and each of the values in that vector are taken from this set of possible values, or our alphabet. Of course, the goal is to find a solution that's close to, or ideally at, the global optimum. And the reason we want to use quantum computers for this is because these problems typically lack exploitable local structure, and they have incredibly large search spaces. So the hope is a quantum algorithm that's able to act globally on the whole problem space. Hopefully we can converge a little faster than we can using classical methods. And the particular type of algorithm that's usually applied to these are these variational algorithms. I think most famously the quantum approximate optimization algorithm, but they all follow this pattern. You have some initial state that you've mapped to basis states of a Hilbert space. You then apply a phase shift to those states that's proportional to the cost of each of the solutions. You then apply another unitary, the mixing unitary, and this couples together those basis states during which the phase encoded costs leads to constructive or destructive interference. And the idea is we can keep repeating, apply these unitaries, the phase shift and the mixing unitary, one after the other. And if we have chosen the right parameters for our phase shift and mixing operations, we'll converge to high quality solutions. And the way we typically find those parameters is using a optimization loop. So we tune our phase shift and our mixing times. Now, there's quite a few challenges when it comes to developing these algorithms. Firstly, they're relying on fairly complex quantum dynamics. It's very difficult to derive general proofs in all but some very specific circumstances. And as we all know, available quantum computing devices aren't production ready. They don't provide a platform for benchmarking these algorithms if you're an algorithms researcher. So really you have to rely on classical simulation, and to get up to a scale where you can actually start to get a sense of how your algorithm is really performing, you need to use supercomputing researchers. Supercomputing, well, yes, but also you need to use supercomputing resources. And one thing I was surprised to learn, when I sort of got into the field, is just because someone has the title, quantum computing expert, it doesn't imply that they're a computing expert. Sometimes, but you normally have people, often the mathematics, the physics, and then you have the computer scientists. Now, If you wanted to simulate one of these QVAs, the sort of standard or most common method is to map your unitaries, so map your phase shift and mixing unitary, and then also your state preparation to a quantum circuit. So that's a expression of those sort of fundamental quantum operations in terms of these fundamental quantum logic gates. So here we're showing a single iteration of a QVA called the QAOA, solving a max cut problem. And we'd see, so they're applied from left through to right. So we've got our state preparation, followed by encoding of our solution costs. Then the mixing operation, and here we're just doing one iteration, and we're measuring our final state. And you would repeat this multiple times to compute an expectation value that will allow you to adjust the parameters. This works really well if you have a cost function that you can use to implement your UQ there that is acting on the same set of qubits as your solution space, right? So here we've got 4 qubits. All of their possible states correspond to a solution. We're able to apply, UQ by acting only on those 4 qubits, and the same with the mixing operation. But really, in practice, we're interested in a pretty wide range of optimization problems, in particular these MP hard problems, where really all we require is that the problem cost function has solutions that are each evaluatable in polynomial time, right? And we know that if we have that property, we're going to be able to compute that, the cost of any given solution using on the order of d qubits to get d bits of numerical precision, right? So from a complexity theory standpoint, simple. From a simulation standpoint, that means introducing another register, so another set of qubits that's on the order of the precision you're interested in. And now we're straight away wandering into a regime where to do an exact state vector simulation, well, it's quickly becoming impossible. Now we could try to construct a circuit that actually computes the costs again directly on, that smaller subspace, but that would be inefficient and not representative of the actual circuit in practice. And really, you'll spend most of your time just trying to build this circuit. So what's the alternative? So alternative is to use a slightly more, traditional approach, this Hamiltonian based simulation, where we're actually just going to, use classical or traditional quantum simulation methods to compute the action of our unitaries on the Hilbert space that we're interested in, so the Hilbert space of our possible solutions. If we take this approach, the mixing unitary, which is this exponential of a diagonal operator, where all of those diagonal elements are our costs, becomes an embarrassingly parallel operation, right? So really great on a cluster. And not only that, you can compute all of your solution costs in MPI parallel really easily. So that becomes a trivial step. The hard step then becomes computing the action of the mixing unitary. So we have off-diagonal elements in that matrix exponential, and the matrix exponential is defined by this infinite but converging time series. So to help researchers perform these kind of simulations, develop this package EuroMPI, or quantum optimization with MPI. And the idea is to give researchers a approachable Python interface to MPI parallelized simulation backends, so they can write simple Python functions to define their cost function, their mixing structure, and various other parts of the algorithm, and then At runtime, the user-defined functions are evaluated at the Python layer, and then all that data is passed off to sort of a more performant backend, and then the simulation will just execute parallel on the cluster. There, this is sort of what the sort of general approach of the software looks like. So it would have these QOP functions that are all definable in the Python layer, and to define a particular type of mixing unitary, they would work with these unitary interface classes, which are coordinated by an ansatz class, and at runtime it figures out a compatible MPI sort of partitioning of your state vector and runs the simulation. Now, that was all simple enough to do really in on a CPU-based system, but with a new generation of clusters, we're interested in using GPU acceleration. So what really brought me here today is to talk about QOP Wavefront, which is a new backend for QOP that is aiming to bring performant GPU accelerated simulation that can work in a distributed memory scenario. So the initial structure of QOP was basically just one MPI process per partition of your state vector, and that doesn't really work in a sort of heterogeneous environment because we've got much fewer devices per per node. But when it comes to the Python layer, I still want the user to be able to use all of the available cores in MPI Pi to compute their mixing structures and cost functions and so on. So they don't really have access to OpenMP, right, unless they want to leave Python. So what we wind up with is a communicator structure that actually sounds quite familiar to some of the scenarios that were brought up yesterday, where we initially determine a partitioning of the state vector over the available devices, and then that is in turn used to determine a node-wise partitioning of the state vector. So then at runtime, we're going to evaluate all of the user-defined functions on that host node communicator, and then transfer all of that information to our devices, after which the simulation can take place entirely on device with GPU to GPU buffer transfers. And to get the data from a process that isn't associated with a GPU, at the moment I'm using inter-process communication context. So just sending that with a blocking send receive and then doing the memory transfer. That's the general setup. And with this, we can initialize the simulation, we can compute the expectation value, compute the state norm to verify the final solution and so on. But we need these MPI parallelized and now GPU accelerated numerical methods. And one of the challenges there is just the sort of HIP and then ROCm based ecosystem isn't quite as mature, right, than either the CUDA or the just CPU based methods. So to realize some of the methods we'd like in the package, we've actually had to take a bit of a detour and do some additional software development. Now, I won't spend too much time on the particulars, but essentially there is a class of these unconstrained combinatorial optimization problems where if you look at those X's there, those are the possible values. And our solution space is basically the Cartesian product, or equivalently the tensor product, of those sets n times for however many variables we have. And you wind up with this big list of solutions where we've just sort of listed the solutions in basically a row major ordering. And if you're trying to design an algorithm to approach this type of problem, a natural choice of mixing unitary is going to connect strongly over each of those dimensions. So there I've sort of shown a tensor product of complete graphs, and the resulting graph structure, or Hamiltonian structure, sorry, is a Hamming graph. So it leaves you with this Hamiltonian that will connect every solution that differs in exactly one of its values. Now, if you want to simulate that type of mixing unitary, you're able to do that using a multi-dimensional FFT. So an FFT over each of those coordinates. And we're able to do that because there's this great relationship between the eigenvalues of a circulant matrix and the discrete Fourier transform. But the challenge faced there is that out of the available libraries that could do this in MPI parallel, none of them natively supported a FFT above 3 dimensions or higher. And we're almost exclusively interested in high dimensional transforms because the advantage of these algorithms increases with the number of dimensions. So to actually get to a regime where these algorithms might stand a chance to perform well, where we need to go higher. So to address this, developed a simple package called Shaft, Scalable High Dimensional Accelerated FFT, which implements a method actually proposed by Dalson et al. And he actually gave a presentation earlier this week, MPI for Pi. And in this approach, the state vectors distributed using a balanced block contiguous slab decomposition, and then we use subarrays with MPI all-to-all W to redistribute the coordinates and then avoid the need for local transpositions. And implemented this using HIP-FFT with the to perform the local transforms. And when we combine that into the communication sort of framework described earlier, found that we're able to get pretty reasonable strong scaling and fairly efficient weak scaling. Now, I'd like to say that's because the GPUs are just busy plugging away at the work, but of course it's a data constrained operation in the end. So really, most of our strong scaling speed up is attributable to a just decrease in the subarray size that we need to communicate. But I think quite fortunately for this type of simulation, because we have this really close correspondence between our simulation method and the numerical, well, the quantum system we're trying to simulate and the numerical method we're using, the communication overhead is actually quite low. So here there is only a sort of 2 distributed coordinates, so you only need 2 redistribution operations, and because of how we've sort of laid them out on the devices in this block contiguous fashion, the amount of sort of transfer between devices that are off the same node is actually fairly minimal. Yeah, so there's a lot more future work, but just the things at the top of the list, there's definitely performance to be had if we were to perform an initial reordering of the global communicator to ensure that GPUs were paired with processors that are in the same NUMA region, and to really reach the same amount of functionality that we have in the CPU-only version of the package, need to implement a method to perform these simulations with sparse unitaries. And hopefully soon, if folks are interested, we'll be putting out a standalone release of Shaft. Thanks.
All right, thank you very much. Are there any questions in the room? I don't know if you have anybody online. If not, Ida, go ahead, please.
So it's potentially a little off topic given you're mostly talking about communication, but I was wondering what your experience has been with using RockFFT on the GPUs. I've used it before and found it was somewhat lacking.
Because I'm working with the the HIP FFT, sort of abstracted away somewhat from Rock FFT. I've found it's worked, fine enough. Give me a decent speed up over just using FFTW. I did run into some issues with sort of larger transforms, and then I think like larger strides. It would fail if the strides were going above the limits of single precision integers, which is a little frustrating. But yeah, that's been my experience so far.
Yeah, if it does turn out to be a bottleneck, I guess is more of a comment. You might consider checking out VK FFT, written in Vulkan Compute at a bit of a lower level than Rock FFT. I found that is better able to handle these weird edge cases of FFTs on GPUs, or at least on AMD.
Right. Heard of it, but this is definitely a motivation to put that in as a possible backend for the FFT library. Thank you.
Any other questions? If not, I was wondering something. You had the combination of all-to-all W plus subarray types, right? Perhaps not the most common combination of things. Have you done any chance to compare different MPI implementations and see how well this is supported? When data types always have been kind of a stepchild sometimes in the implementations.
Not as of yet, but very interested at looking into that. There was some, of course, benchmarking results in their original paper, but it'd be really interesting to see, because the paper was out in 2018, really interesting to see if that's changed or developed over the intervening years.
Thanks. All right, any other questions?
Yeah, thanks, Edric. So I saw that in your tests, in each node, you were using the 8 GPUs, but also 16 MPI ranks in each. So can you explain why?
Yeah, good question. So the number of MPI processors used at that Python layer is a balance between the amount of time you're going to spend computing the solution costs and other data structures, and then the overhead incurred in the transfer the data from the host to the device, because we have a bit of a bottleneck so we're using these inter-process communication handles. Now, for these benchmarks, it's just setting the solutions or the costs to a constant NumPy array. And in that scenario, compute's quite low. So it turned out that 16 was actually a good balance for those nodes. In general, for more complicated costs, you'd maybe want to up that count.
You can do one final question.
Thanks for the talk. Just one comment and a question. I am interested in the data type performance and how that works with all-to-all. So I'm happy to collaborate, especially if I think we have some work to do in OpenMPI in combination with accelerators. You mentioned that right now you're computing on a dense matrix, basically, or dense tensors.
Essentially, yes.
How sparse are they in reality?
So in this case, the tensor, so that's our state vector, is quite dense. Essentially, we've got a sufficiently complicated optimization problem that phase encoding leads to, basically you have a unique phase value for every, element in that state vector. So it's completely dense. From the perspective of the quantum simulation, it's really nice though not having to ever represent the Hamiltonian. So it's really just vectors the whole way. But yeah, would love to talk more about the data types and benchmarking there.
Thank you.